The second part of chapter 2 is exactly the same as the first part, except with a Gaussian instead of Bernoulli distribution. So we'll have the samples of y that are Gaussian with mean mu y and variance sigma y squared. And then we'll have the x's as well with possibly their own parameters. And the null hypothesis is going to focus on the means. Okay? Versus the alternative that they're different. Sometimes we also assume that the variances are the same, which is called a pooled analysis. But that's not what I'm going to do here, although you can find a bit about that in the book. So I'm going to assume an unpooled analysis for this vignette. Simulation is just like two copies of what we did in chapter 2, so it's going to be just like we did a moment ago if you were just watching part A of the videos. So let's go over to R immediately and just jump in and do that. So here's data from chapter 1. These are the heights of women from my class, and remember we calculated y bar and S2, so I'm going to calculate those. This is basically how we summarized it before, only now I'm putting a little y on my S2 to keep track of the y population estimate of variance. Now here's a second set of data. Oops, it looks like I mistyped the name of my town. So we're going to compare this to data that's collected from the Blacksburg High School women's basketball team. These are real data. You can find a link to that in the book. We'll call that X, and we'll summarize the X's in exactly the same way. Okay? Ignore this paired t-test thing. We're going to come back to that a little bit later. I just wanted to have that there for later. Okay? So a sensible test statistic, I should have written that down before I got started. Just like in part A of the vignette, a sensible test statistic is the difference of the two means. So mu hat y minus mu hat x. So we could call that mu hat delta, just like the theta hat delta. And of course, that's y bar minus x bar, right? So I could calculate mu hat delta as the difference of y bar minus x bar. And if the null hypothesis is true, this number should be close to 0. How can we tell? We can do a simulation. Okay, so I'm going to do the usual scaffolding for a simulation. Okay, and then I'm going to do 2 copies of what we did in, well, I said chapter 2 a moment ago, but we learned how to do it better in chapter 3. So I'm actually going to follow the simulation from chapter 3, which involved sampling sigma 2y values from an inverse chi-squared so that we can do the t version of this test. Okay, so that's for the y variances, and then we use our norm with ny samples and a mean of mu. We have to pick a value of mu for this simulation. It really doesn't matter what you pick. In the book I picked 10, sorry, in the book I picked 7, but here I'm going to pick 10. It really doesn't matter. What matters is that you use the same value for the y population as you use for the x population. And you can watch me, I'm going to do that. So I'm going to do r norm mu and then square root of sigma 2y. So that gets me a sample from the y population. Oops. And then I can sample from the x population in a similar way. And then I can calculate their difference. Whoops, I forgot to do the R norm. So okay, better make some space for this. Okay, so see how there's one copy of chapter 3's simulation of y values under a Gaussian distribution and another copy, and then I calculate the difference in their means. Okay, so I apparently have a typo somewhere. There we go, that fixes it. N not found. So where am I using a little n? Here. Oh, great. Okay, so that covers the simulation, and then we can visualize the same way we usually do. And you can't see that, but you should be able to now. So those are the samples of the mu hat deltas that I would get if the null hypothesis is true. What does that mean? I put the same mu value in for the two Gaussians, and when I do that, the difference in their means tends to cluster around 0, as you might expect. And then I can put on that the value of mu hat d that I calculated from the data. Okay, there it is, and then we can decide if that is a typical value under that distribution. To me, it looks kind of borderline. It's a little ways out into the left-hand tail. If I want to be precise with a p-value calculation, I can do 2 times mean of mu hat, oops, less than or equal to mu hat d. And I get that that p-value is bigger than 5%. So bigger than 5%, so can't reject the null hypothesis, which is that mu y is equal to mu x. So it seems like the women in my class have the same average height as the women on the basketball team. It was a close call, but I can't detect the difference between those two statistically. Okay, that was by simulation. How do I do it in closed form? Well, this is kind of a complicated story. There's a lot more detail on this story in the book, but I'm just going to summarize for you here that Welch, so this is known as the Welch test, or a two-sample t-test, in 1938 showed that the difference in y bar and x bar, so y bar minus x bar, divided by their standard errors, Right, so I'm just using that sums of Gaussian are Gaussian here and pulling the variances or summing the variances of those two. That is usually called a t-statistic because it has a t-distribution with a degrees of freedom nu that is approximately the minimum of ny and nx minus 1. There's actually a more accurate calculation that you can find in the book for this value. And this and this is a good approximation. And the book goes on to explain the way in which it's an approximation. You always have the central limit theorem or the asymptotic distribution of the MLE to get a Gaussian approximation, but this one's a little bit better because it acknowledges the chi-squared distributions of the estimated variances sy squared and sx squared. Okay, so how can we use this? Let's pop back over to R. So I can calculate the squared standard error as sy squared over ny plus sx squared over nx. Right, so that's following the denominator. Oops, I don't have an sy squared. Oh, I called it s2y, sorry. Not sy2. I don't know why I inverted those. Okay, that's what you get for recording live. The standard error is the square root of that. Okay, and then my degrees of freedom is the minimum of ny and nx minus 1. Again, that's not quite right, but it's good enough for this live example. Keeps it kind of simple. And then the p-value is 2 times pt minus absolute value of the, oh, I didn't calculate the t-statistic. I got a little ahead of myself. The t-statistic is y bar minus x bar divided by the standard error. And then I can do that with new degrees of freedom. So you can see how this value that we calculated using the Welch test is very similar. In fact, they round to the same 100th place as the simulation that we did. So that's called the Welch test, or it's one variation on a 2-sample t-test. Now I'm going to get to this thing that's waiting here in the R code. I want to tell you what a paired t-test is. Okay, so an important variation involves what's called paired data. Okay, so this is where the data really come in pairs. And in particular, we have the same number of them, the same number of x's as y's, and that number is n. So we're going to look at an example in a moment where we're going to use the same y's as before, but the x's are going to be the heights of the moms of the y's. So those were the women from my class. Okay, so we're not going to quite do the R yet, but that's going to be our motivating example. Are we able to detect that there's a difference in heights between these daughters and mothers? Here's a kind of a cool trick. So we can reduce this this 2-sample testing problem into a 1-sample one. So let's let di be the difference between yi and xi. I don't know why I wrote that. The difference. Okay. We can study that as Gaussian. If we assume that the individual populations are Gaussian, then their difference is also Gaussian. And it'll have some mean mu, or mu d, and variance sigma d squared for I equals 1 up to n. And then to detect any differences in the means, I could, if we're thinking about mu y and mu x, which I didn't really write down, but we were talking about that earlier, that's basically the same as mu d being 0, right? If the means are equal to one another, then the mean of their difference is 0, versus the alternative hypothesis that their difference is not 0. And we already know how to answer this question using a one-sample t-test. So we do a one-sample t-test on these differences. Okay, so let's do that in R. So here are the heights of the moms, and we should have the same number of those as we had the original y values. And I always like to look at those as a data frame with two different columns. I just think this is a nice way to lay it out. It's not important for actually doing the calculations, but this lets me see the pairs in the rows. So this is a daughter and a mother. The daughter is taller than the mother. Daughter and mother again. Daughter is taller than the mother. Daughter and mother again. Here's two that are the same height. Okay. Okay, so now I'm going to create the differences. Whoops, I meant to be typing up here. Okay, so these d's are going to be y minus x. So it's like I have a totally new data set of differences. And then I have n of them, which should be 24. Okay, so those are my 24 differences. And how do I do the analysis? I can choose to simulate or do the math way. I'll skip the simulation. You can try that on your own, and I'll just do it the math way. So d bar is mean of d, so that's my estimate of the mean. And then my estimate of the variance is S2D, and then I can calculate the standard error. So the standard error is the square root of the estimate of the variance divided by n. And then my t-statistic is the estimate minus the thing you want to know, which is 0. So I don't need to put the 0 in there, divided by the standard error, and then I can calculate the p-value. With n minus 1 degrees of freedom. So this p-value is really small. This tells me that I can reject the null hypothesis that mothers and daughters have same mean height. Okay, so that's a paired t-test. So you've seen two different kinds of t-tests. One of them is the Welch test, which is for unpaired data, where I can have different numbers of y's and x's. And then we saw the paired t-test, which is for matched pairs, the same number in each group. We can do that one by reducing it to an ordinary t-test on the differences.